Stage 3, which is known as formation of atoms and cosmic transparency. About 3 lakhs years after the initial expansion, temperatures dropped to around 4500 Kelvin. This cooling allowed electrons to combine with protons and form stable neutral atoms in a process called recombination. As a result, the universe changed from an opaque plasma to transparent state, since photons could now travel without constant scattering. The release and movement of photons as faint glow gave the cosmic microwave background radiation, which is detectable even today, gives a strong evidence of Big Bang theory. Chronological phases of the universe's development. First one is the Planck epoch. The time period is 0 to 10 to the power of minus 43 seconds. In the universe's earliest instant, known as the Planck epoch, all 4 fundamental forces like gravity, electromagnetism, the strong nuclear force and the weak nuclear force were likely unified. During this time, the universe was so hot and dense that conventional physics cannot describe it, leaving this period beyond the limits of our current theories. The second is the Grand Unification epoch. After the conclusion of the Planck epoch, the universe experienced a rapid decrease in temperature, which allowed gravity to become a distinct force separating from the unified state it had shared with the other fundamental interactions. At this stage, the strong nuclear force, weak nuclear force and electromagnetic force still exist in a combined form. During this brief but critical period, the universe was characterized by extremely energetic collisions among elementary particles. These high energy interactions were crucial as they laid the groundwork for the subsequent formation and evolution of matter by establishing the basic properties and distribution of the particles that would later assemble into atoms and larger structures. Next stage is the inflationary epoch. The period is 10 to the power of minus 36 to 10 to the power of minus 32 seconds. In this brief but critical period, the universe experienced an enormous exponential expansion. Inflation stretched minuscule quantum fluctuations to cosmic scales, creating density variations that eventually formed stars, galaxies and clusters. Next is the electroweak and quark epochs. As cooling continued, the strong nuclear force split from the electroweak force during the electroweak epoch. Soon after, in the quark epoch, quarks, gluons and other fundamental particles began to exist independently in a superheated plasma. Next is the hadron and lepton epochs. During the hadron epoch, the universe had cooled sufficiently for quarks, the fundamental constitutions of matter, to bind together, forming protons and neutrons through strong nuclear interactions. These newly formed hadrons becomes the essential building blocks of atomic nuclei, setting the foundation for all later atomic structures. Later, as the universe was continued on expansion, it also cooled. It transitioned into lepton epoch. In this phase, the heavier hadrons became less influential, but the light fast moving particles like electron, neutrons and positrons dominated the universe as they started traveling, and the energy exchanges and interactions during this period were primarily governed by these leptons, which played a crucial role in shaping the universe's thermal and particle evolution leading up to nucleosynthesis. Next is nucleosynthesis, that is 3 minutes after the Big Bang. Within 3 minutes of the Big Bang, temperatures started to drop, which led to the fusion of the protons and neutrons into first atomic nuclei. This process is known as nucleosynthesis. This fusion produced hydrogen, helium and traces of lithium. the photon epoch. During the photon epoch, the universe was filled with a dense, hot plasma of matter and radiation. Photons interacted continuously with electrons and protons, preventing light from travelling freely and making the universe opaque. Let us have a next stage, recombination and decoupling, that is around 3,80,000 years later. Around 3,80,000 years after the Big Bang, the universe cooled to around 4500 Kelvin. Electrons combined with protons to form neutral atoms, a phase called recombination. This decoupling of matter and radiation allowed light to move freely, releasing the cosmic microwave background and the afterglow of the Big Bang. Next stage is the dark ages and birth of the first stars. After recombination, the universe entered the dark ages, a period without stars or galaxies, dominated by neutral hydrogen gas. Hundreds of millions of years later, gravity pulled matter together to form the first stars, ending the dark ages and triggering cosmic reionization, which changed the universe's structure and chemistry. Let us have a discussion on galaxy formation and modern cosmic structures. Over the course of hundreds of millions of years, the force of gravity continued to draw together gas, dust and dark matter, leading to the gradual emergence of increasingly complex cosmic structures. Matter coalesced into vast formations, giving rise to galaxies which themselves organized into clusters and even larger superclusters, which formed the large structures of the universe. Within the grand cosmic architecture, the Milky Way galaxy began to form approximately 13.6 billion years ago. Much later, about 4.6 billion years ago, a dense region within one of the Milky Way's spiral arms collapsed under its own gravity, forming the Sun and the surrounding protoplanetary disk. From this disk, the planets including Earth gradually accreted, creating a solar system capable of eventually supporting life as conditions on Earth stabilized and evolved to allow biological process to begin. Let us have evidences which are supporting the Big Bang theory. First is cosmic microwave background radiation, which is known as CMB. The CMB is faint glow microwave radiation that is present in the entire cosmos. It is the leftover heat from the early universe dating back to around 3,80,000 years after the Big Bang during the recombination epoch. At this stage in cosmic history, the formation of the hydrogen helium occurred. This process known as recombination, which allowed photons to decouple from matter and move unhindered through space, and this has enabled the travel of light freely for the first time, which later filled universe with the cosmic microwave radiation in the background. Arno Penzias and the Robert Wilson discovered the CMB in 1965 when they encountered an unexplained persistent signal in their radio antenna. This discovery was a breakthrough, providing concrete evidence for a hot, dense origin of the universe. The CMB's nearly uniform temperature of about 2.725 Kelvin, along with tiny variations mapped in detail by experiments like COBE, WMAP and Planck, matches precisely with the Big Bang theory predictions. These small fluctuations represent regions of different densities that evolved into the large scale cosmic structures we see today.